We are dealing with part 2 of our revision thermodynamics paper for Diploma in Mechanical Engineering. The paper was written in April 2025. So in part 1, we moved from question 1 all the way to question 4, meaning that today we are going to start from question 5 all the way to question 8. With that, let's get to work. So question 5 to question 8, that's our task. Let me quickly take us just to that part. Question number 5. I believe it's this one here. Okay. So here's our question 5. It says, in a steady flow open system, a fluid substance flows at a rate of 4 kg per second. It enters the system at a pressure of 600 kilonewtons per square meter, velocity 220 meters per second, internal energy 2,200 kilojoules per kg, specific volume 0.42 cubic meters per kg, leaves the system with a pressure of 150 kilonewtons per square meter, velocity 145, internal energy 1650, specific volume 1.5. During its passage through the system, the substance here is not just a loss, it should add something. It should be the substance has a loss during its passage through the system. So during its passage through the system, let me just correct that part. During its passage through the system, the substance has a loss by heat transfer of that much. 40 kilojoules per kg to the surroundings. Determine the power of the system, stating whether it is to or from the system. Neglect any change of gravitational potential energy. When you have a question like that, you have to arrange data specifically for inlet and also for the exit side so that there is no confusion between the two sets. So on the inlet side, our pressure number 1 is 600 kilonewtons per square meter, velocity 220 meters per second, internal energy 2,200, specific volume 0.42, heat loss. So this negative wasn't in the question, it's the language which said has a heat transfer loss by, then they give us that. So it means we're using a negative. On the exit side, we have the pressure number 2, 150 kilonewtons per square meter, velocity 2, 145, U2, 1650, and specific volume number 2, 1.5 cubic meters per kg. This is the question that is inviting the steady flow energy equation. Steady flow energy equation, C1 squared over 2 plus U1 plus P1 V1 plus Q is equal to C2 squared over 2 plus U2 plus P2 V2 plus work done. So all we are going to do is just to substitute. C2 is 220, so 220 squared divided by 2 multiplied by 1,000. This 1,000 is not up there. And the operation there is just for converting from joules to kilojoules. That's all. Because when you calculate in this format, when you go ahead and calculate it like that, you end up with the kinetic energy being in joules. Of course, because we're dealing with 1 kg, it's now joules per kg. Then U1 was 2,200. Pressure 1 was 600. Specific volume 1 was 0.42. Heat, this is the one where I told heat transfer loss, negative 40. Equals, we proceed with V2 is 145. So we squared divide by 2 times 1000. Now look at it again. We're saying the same thing we picked there. That's what we're having there. We are simply converting from joules to kilojoules, hence the introduction of this 1000 here. Plus, there, this is U2, 1650. Plus, again, pressure 2, 150 times specific volume number 2, 1.5. And finally, plus work done. So the work done is 550.6875 kilojoules per kg. What about the power? The power is work by mass flow rate. Work multiplied by the mass flow rate. So the work is 550.6875 times our mass flow rate, which is 4. Then our power is 2,202.75 kilowatts. The question was asking us to specify whether it's from or to. So for the language we've picked, this is the system has done, the power is coming from the system that's produced something which can be used outside. So this is the power from the system because it's coming from that system. B says air passes through a gas turbine system at a rate of 4 kg per second. It enters the turbine system with velocity 90 meters per second, specific volume 85 cubic meters per kg, leaves the turbine system with specific volume 1.45 cubic meters per kg. The exit area of the turbine is 0.038 square meters. In its passage through the turbine system, the specific enthalpy of the air is reduced by 200 kilojoules per kg, and there is a heat transfer loss of 40 kilojoules per kg. Determine the inlet area of the turbine in square meters, exit velocity of the air, meter per second, and power developed by the system. Information provided: the mass flow rate 4.5 kg per second, velocity 1, C1, 90 meters per second, specific volume number 1, 1.45 cubic meters per kg, exit area 0.038 square meters, enthalpy at inlet 200, enthalpy at exit 0. How do we know? This is just saying reduced by. When you say it has been reduced by, you're simply saying your change in enthalpy is equal to the final enthalpy to get your change minus the initial enthalpy. This is your change. The general formula for change is that number you have, negative 200. Now, there are so many smart ways of doing this, but the one I find much easier to pick up is that for you to achieve this, it means you should have put a 0 here and a 200 there. So that if I say 0 minus 200, my result is that. Telling me that for this one, this is my H2 and this is my H1. So the H1 is 200, the H2 is 0. You start with 200, you end up with 0. That's a reduction. So that's what we are seeing there. H1, 200, H2, 0. Then heat transfer loss, that's negative 40 as kilojoules per kg. Inlet area. So this is the formula we use. A1C1 is equal to mass flow rate times specific volume number 1. We make area the subject. We have mass flow rate times specific volume 1 divided by velocity 1. So that being the case, then area 1 is equal to 4.5 times 85 divided by 90. So with that, then we can say our area 1 is equal to 4.25 square meters. Exit velocity of the air in meters per second. So the same formula now on the exit side, 2. Area 2 by velocity 2 is equal to mass flow rate times specific volume 2. Again, we target what we're looking for, which is C2. It's equal to mass flow rate times specific volume number 2 over area 2. In our substitution, the mass flow rate is 4.5 by specific volume number 2, 1.45, divided by area 2, which is 0.038. Result, 171.71 meters per second. Power developed by the turbine system in kilowatts. So here we simply say C1 squared over 2 plus H1 plus Q is equal to C2 squared over 2 plus H2 plus work. The other version of the steady flow energy equation. And we can do the substituting. C1 is 90. So 90 squared over 2 multiplied by 1,000. So this is like 2,000 plus H1, 200 plus Q, 40 equals 171.71 squared over 2 times 1,000 plus 0. Then say plus what we're looking for, which is W. So the moment you make this W the subject, you end up with 149.308 kilojoules per kg. Now, power is supposed to be mass flow rate times whatever result we have there. So 4.5 times the answer we got, 4.5 times 149.308. Result is 671.885 kilowatts. That is the power. Question number 6 starts with the definitions, fuel and combustion. Combustion, process where the fuel reacts with oxygen to produce heat energy. The other one is a fuel where the process we've talked about, the substance that is involved is a fuel, which reacts with oxygen to produce heat energy. Now, here's our question. A fuel consists of 22% carbon, 20% hydrogen, 8% oxygen by mass. Determine the stoichiometric mass of air required to burn 1 kg of this fuel. Carbon, 72%, 72 over 100, which is like 0.72. Hydrogen, 0.2 kg. Oxygen, 0.08. So here we're saying 72 divided by 100. That's how come we have 0.72. 20%, which is 20 over 100. 20 divided by 100. So we have 0.2. 8% for oxygen. 0.08 comes from 8 divided by 100. So hence we have this one. Let's start with oxygen. The mass of oxygen required. So here, when you refer back to how much oxygen is needed to burn 1 kg of carbon, you realize it's this from the chemical equation, 2.667. And it's as simple as you write the chemical equation for carbon, C plus O2, giving us CO2. That's the complete combustion of carbon to carbon dioxide. So carbon The atomic mass is 12, so we have 12. Here you have 2 oxygen atoms, and its atomic mass is 16. So 16 times 12, 16 times 2, giving us 32. 32 there. What is here is what is there, because this is a balanced equation. So 12 plus 32, the end result is 44. 44 kg of that. So by mass, that's what you have. And all we did to arrive at this was now take the mass of carbon, divide through. This is divide by 12. And even here, divide by 12. So, and this is where the secret is. Even on the other end, for the products, you also divide by 12. This part will produce a 1. But our mainstay is here. 32 divided by 12. The answer is this. 2.667. If you write the other one for hydrogen, where you're talking about the complete combustion of 1 kg of hydrogen to water vapor or to water, you find that upper penaplism over 8. You end up with 8 kg. So meaning that 8 kg of oxygen is needed to burn 1 kg of hydrogen to complete the combustion into water vapor. So that's why for this part, we bring in 8. So 0.2 times 8. And the next thing we have is 8%, 0.08 times oxygen. Oxygen, you cannot burn it. Instead, it's the one we're looking for in the air. So we subtract any amount of oxygen already present in the fuel. That's why we decide to multiply by -1. Why -1? -1 is not going to change this value. It will just introduce the negative sign, which is as good as subtracting. With all that, we can now say, let's sum up, add this plus that plus that. The result is 3.44 kg. The answer we found, the 3.44, just divide by 0.23. Meaning we're saying the stoichiometric mass of air needed is supposed to be total mass of oxygen divided by 0.23. In this case, we had 3.44 for this area. This is the one we just have right here. And then divide by the number we've talked about, 0.23. A quick question. Why 0.23? Because 23% of air, 23% of this air is oxygen. So, hold on now. Put there. 23% of that air is actually oxygen. So, if you now want to transpose it, to take it back to 100%, that's why we're saying 0.23, or total mass of oxygen divided by 23%, or the same 0.23. By mass, air contains 23% oxygen. The other 77% is actually nitrogen. So when you do the division, 3.44 divided by 0.23, the result is here. You have 14.96 kg. Why are we saying per kg fuel? Basically, if you check carefully, it's like we're even already giving the air fuel ratio. You need 14.96 kg of the air to burn 1 kg of fuel. So if by any chance the question had decided to ask for the air fuel ratio, you would take this number and set to 1. This is per kg. 14.96 to 1. That is our air fuel ratio. However, here it was just asking for the mass of air required for the burning of 1 kg. And that's our answer. Here's an interesting one now. We're dealing with, it says, determine the stoichiometric mass of air required to completely burn 1 kg of heptane. Heptane is C7H16. So C7 means that we have 7 atoms of carbon. Then 16 under H, we're saying H16 is giving us 16 atoms of hydrogen. So let's get the relative molecular mass, meaning let's get the total mass for all these. 7 atoms of hydrogen times the atomic mass for the hydrogen. So 7 times 12. We do the same for hydrogen. 16 of those atoms times the atomic mass for hydrogen, which is 1. When you do that, you end up with 100. This is the total. So when we say let's find the mass of carbon, we'll say we'll pick carbon. Carbon has 7 atoms. 7 times 12 is atomic mass. Divide by the total. So that's why we have 84 over the total, which is 100, giving us 0.84. The same procedure for hydrogen, 16 hydrogen atoms. So 16 times 1, divide by the total, which is 100. So 16 over 100, giving us 0.16. Then we repeat the process. First, carbon, we said the mass of carbon, the mass of oxygen needed to burn 1 kg of carbon is 2.667 as picked from the chemical equation. So what is present? How much is present for carbon is 0.84. So 0.84 times 2.667, giving us 2.24028. Then how much of hydrogen we have is 0.16. We multiply by the mass of hydrogen, right, the mass of oxygen needed per kg, per 1 kg of hydrogen to be completely burnt, which is 8. So 0.16 times 8, we have 1.28. This question, smart as it was, it only had 2 elements. So meaning that we can here demarcate. So 2.24028 divide, we add with, we are going to add this. There's also 1.28. And the result is 3.52028. Since we've now found the total mass of oxygen needed, we can go back to the same process we started with, which is the total mass of oxygen needed divided by 23%, or divided by 23 over 100, which is 0.23. For the reason that 23% of air by mass is oxygen. So that's why we now want to review how much air then is present here. So 3.52028 divided by 0.23. Stoichiometric mass of air, therefore, comes out as 15.3056 kg per unit mass of fuel. So that is the mass of fuel we need to burn 1 kg, the mass of air required for us to burn just 1 kg of this heptane. Oh, let me, okay. The next question, this is now question number 7. Question number 7 says the capacity of a 202 TR. The capacity of a 200 TR refrigeration when working between -6 degrees Celsius and 25 degrees Celsius. That's the capacity. It's 200 TR of that refrigerator. Then determine the mass of ice produced per day from water at 25 degrees Celsius. Also, calculate the power required to drive the unit. Assume that the cycle operates on a reverse Carnot cycle and latent heat of ice 335 kilojoules per kg. Now, one thing you will notice about this question before we even go into the data is that there are two things that have not been given, which are very important. We've only been given the latent heat of ice. Are we saying that we're going to ignore the heat required to lower down the temperature from 25 to 0? Practically, it's a no. But here, we're going to assume that we will produce ice at 0 degrees while operating between those two temperature limits. With that, let's get to work, meaning that if you decide to follow this question and ignore the 25, then it means you focus on latent heat and get your answer like that, which will probably be slightly lower. So here, let's go to the capacity of the refrigerator. The refrigerating capacity given in terms of refrigeration is Q 200 TR. So let's convert it to the normal, the SI unit. 1 TR is 3.516 kilowatts, meaning kilojoules per second of heat. So since there are 200, we multiply 200 by 3.516, giving us 703.2 kilowatts. That is the capacity. That is the capacity. Meaning we have that as our capacity for this refrigerator. Evaporating temperature, -6 degrees Celsius. That's the evaporator temperature to our advantage because it's supposed to be much, much lower than what we're targeting. Then we just convert that, it becomes -6 plus 273, giving us 267. Condenser temperature, which is now on the high side, it's 25 plus 273, and we have 298. So meaning here we're just emphasizing that the temperature of the water is actually 25 degrees Celsius. Latent heat of ice is here, which is 335 kilojoules per kg. Now, let's start looking at the mass of ice removed per day. So first of all, let's ensure that we convert the ice from water at 25 degrees Celsius to that ice at 0. So the heat that is going to be removed per kg of water, starting with lowering the temperature, is just, we start with the cooling water from 25 to 0. This will require us, in fact, let me just do this so that we make it neat. So for us to do that, we include this, just a quick one because needed to plant that formula there. Okay, good. Okay, good, this is fine. So what we are saying is that when you look at this one, I'm going to say that this Q1, which is the heat needed to convert or to move from 25 coming down to 0, we'll need to say mass of that substance, which in this case is the water, times the specific heat capacity, times the change in temperature. So this change in temperature will be T2 minus T1. So T2 minus T1. And of course, we'll plant those temperatures there. So we have T2, take away T1. And this is our heat, number 1. And it sits there like that. So with this, we can now start substituting. The mass, it's per kg, so it's 1. And that's why it's not even showing there. Then next, it's the just a minute. The next one is the specific heat capacity for water. This is 4.187. And then we multiply by the temperature difference, which is 25 minus 0. Basically, we're just multiplying 4.187 times 25 to give us 104.675 kilojoules per kg. With that in mind, we can now say we found this. That's our heat energy required to bring down the temperature from 25 degrees Celsius to 0. Now, the moment you bring the water to 0, it's not ice, it's just water. This is not ice, it's just water. Now, what are you going to need to convert this water to ice? You will need latent heat of fusion. The latent heat of fusion per kg, the number given was 335. And since we're dealing with 1 kg, we'll just say 335 times 1. So 335 multiplied by 1. And hence, it remains like that, unchanged. So what do we need then? We're going to add latent heat per kg of water plus that heat we have used to bring down the temperature from 25 to 0. So Q1 plus Q2 is what we're dealing with, giving 104 plus 335. And the heat that is going to be removed per 1 kg of water becomes 439.675. Now, that being the case, then we now move to the part where we're saying the capacity of this refrigerant, this refrigerator, QL, is 703.2 kilojoules per second. Now, per day, because the capacity was 200 TR, we multiplied by the 3 point, that which was the standard for TR, got 703. Now, since this is per second, we need to know in 1 day, how much can we get rid of? So in 1 hour, we have 3,600 seconds. A day has 24 hours. So 36 times 24 times 703.2, giving us 60,756,480. That is the capacity it has. Now, the calculation we've just done is giving us the amount of heat energy we're removing, the amount of heat energy that needs to be removed. So we are going to say the capacity per day divided by that heat, that energy that we are dealing with. So 60,756,480 divided by 439.675. This was kilojoules per kg. So as a result, the mass that you end up with, just the mass in kg, when we divide the two, it's 138,184 kgs every day. This is mass production. It's quite some heavy refrigerant, refrigeration, the heavy fridge working there. Then let's talk about the power required to drive the unit. The power required to drive this unit comes, you start with the coefficient of performance of the refrigerant. Then, of course, this is in a reversed Carnot cycle where we twist them around. So the low temperature divided by the high temperature minus the low temperature. So the lower temperature is 267 divided by the high temperature is 298 minus the same 267. Our coefficient of performance, therefore, is 8.613. The other version of this COP is heat on the lower side divided by the power that we're spending. Heat divided by the power that we're spending equals the coefficient of performance. So then the heat is 703.2. It's the heat that we're getting rid of. Then the power, the net power, we don't know. So what are we going to do? We just cross multiply and make our power the subject of formula. As a result, you notice that the net power is 81.64 kilowatts. B. Two-stroke cycle engine of a large ship has 8 cylinders, each of 850mm bore with a stroke 2200mm. The brake mean effective pressure of each cylinder 15 bar, and the engine runs at 95 revs per minute with specific fuel oil consumption of 0.2 kg per kilowatt hour. The calorific value of the fuel is 43 kilojoules per kg, 43,000 kilojoules per kg. Determine the brake power of the engine, the fuel consumption of the engine, the brake thermal efficiency of the engine. Let's talk about the number of working strokes, which is small letter n. This is supposed to be equal to capital N, engine speed times number of cylinders for a two-stroke cycle engine. If it was a four-stroke cycle engine, we should have divided this by 2. So N, according to the question, is 95. Where is it? Where is it? It's here. Times number of cylinders, which is 8, giving us small letter n as 760. What is called the bore is the diameter of the cylinder. So we use it to find the area. Pi times 0.85 squared over 4. The answer is 0.56745 square meters. Length of the stroke is 2,200 millimeters, which is 2.2 meters. Brake mean effective pressure, 15 bar. Bar to kilopascal, we multiply by 100. So that's why you are seeing we've just written 1500 kilopascals. Just supposed to add a kilo there. Let me put it. It's not a big deal. Specific fuel consumption, 0.2 kg per kilowatt hour. And hence, of course, we've written back our CV, 43,000 kilojoules per kg, and hence completes the data. Brake power of the engine in megawatts. So our BP is brake mean effective pressure times area times length of the stroke times number of working strokes over 60, because the engine speed was in revolutions per minute. So that's why we've included that 60. So then we substitute BMEP 1500 times area 0.56745 times the length of the stroke 2.2 times the number of working strokes 760, divide everything by 60. End result is 23,719.41 kilowatts. So in short, take it to megawatts according to the instructions. It's we divide that by 1,000, so we have 23.72 megawatts. Because this was already in kilowatts. What about the fuel consumption of the engine in tons per hour? So, first of all, the fuel used, we just multiply the fuel used or fuel consumption per hour times that power. Things will cancel themselves. So 0.2 times 23,719.41. These are supposed to be in kilowatts, so they cancel. You remain with 4743.882 kgs per hour. Just in kgs, the mass of fuel being used. Then fuel used, all we do to convert it now to tons, we are going to say fuel used per hour times power over 1,000. So meaning whatever answer we've gotten, this this same value we have, just divide it by 1,000 so that we can convert from kgs to tons. So 4743 divided by 1,000. So we have 4.74 tons per hour. Brake thermal efficiency of the engine. Now, this one requires us to tread with a bit of some caution because we need now to put back the fuel used per second in the expression, because this is now dealing with fuel consumption per second, because that's power. So what we are going to do is to invite the fuel used per hour and divide by 3,600 so that we can convert it to how many kgs are being consumed in 1 second. So we say 4743.882 divided by 3,600. The result is 1.318 kgs per second. Therefore, the brake thermal efficiency is equal to brake power divided by a calorific value of the fuel times the fuel used per second. Express that as a percentage, as you multiply by 100. So the brake power was 23,719.41 kilowatts divided by the CV was 43,000 kilojoules per kg times 1.318. Then whatever comes from there times 100. And hence our brake thermal efficiency is 41.85%. Let's go for the last question. Define the following terms, or rather define the following modes of heat transfer: conduction, convection. In conduction, this is where heat is transferred through the solids without any movement of the substances or through the vibration of those particles in such substances. Convection is a form of heat transfer requiring the complete movement of fluid from one point to another, thereby transferring the heat. So here's our main question. It says we have a 100mm diameter steam main covered by 2 layers of lagging. The inside layer is 40mm thick and has a coefficient of thermal conductivity 0.07 watts per meter Kelvin. The outside layer is 25mm thick and has a coefficient of thermal conductivity of 0.1. The main conveys steam at a pressure of 1.7 megapascals with 30K superheat, 30 Kelvin superheat. The outside temperature of the lagging is 24 degrees Celsius. If the main is 20 meters long, determine the following, neglecting the temperature drop across the steam main: heat loss per hour, interface temperature of the lagging. So the first thing we're going to do is to pick up the diameter of the inner, the inside diameter, meaning we convert it now to radius. So this 100 divided by 2 gives us 50. This is 0.05 because we've converted it to our meters. The thickness, the inner thickness, we're told is 40 millimeters, which is 0.04. Meaning that radius number 2, adding to the thickness, we're going to say this T1 plus R1 to get to that radius. So 0.05, add the thickness, which is 0.04. We have 0.09 meters. Moving from here, from 0.09, which is radius 2, we have to add this thickness, which we were given, the 25 millimeters, which is 0.025. So 0.09 plus 0.025, giving us 0.115 meters. And from that addition, we have R3. Then K1, which is the inner one, 0.07. K2 for the outer material is 0.1. watt per meter Kelvin. Then the pressure of that steam flowing in the pipe is 1.7 bar. Now, here's the thing. When you go into Rogers and Measure tables, those steam tables, check for that, the temperature. The first thing you are going to do is we include this condition provided, 30 Kelvin superheat, meaning 30 units added to the saturation temperature. If you go into the tables, pick 1.7 bar, you will find that the saturation temperature is this, 204.3 degrees Celsius. So what do? Add 30 units to that. So 204.3 plus 30, giving us 234.3 degrees Celsius. Then we also have the outside temperature, which is T2, is 24 degrees Celsius. The length of the pipe, 20 meters. Heat lost per hour. First of all, we're going to find the heat lost per second, which is Q dot. The formula is 2 pi L T1 minus T2, the temperatures, divide by natural log R2 over R1 over K1 plus natural log R3 over R2 over K2. So we start 2 pi times the length of the pipe is 20 meters. Temperature number 1, which is the high temperature where the heat is coming from, is 234.3. Minus the other temperature on the outside is 24. So minus 24. Divide by natural log R2, we said is 0.09, R1 0.05. Divide by K1, which was 0.07, plus natural log 0.115 over R2, which is 0.09. Divide by K2, which is 0.1. So when you compute this, the result is 2436.074. Heat lost in 1 hour is going to be that answer we've gotten times the number of seconds in 1 hour, which is 3,600. So Q dot times 3,600, giving us 2436.074 times 3,600. We have 8,769,866.253 joules per second. That is how much heat you are losing per hour, not per second. So let me just correct that. That is heat lost in every hour. Okay, let's pick up now the other part. The other part was saying heat lost. Sorry, not the heat lost per hour. The interface temperature. This is a repeat. Sorry, I think it has gone back a bit. The interface temperature of the lagging. So one thing you'll notice is that T1, where the heat is coming from, it's at a higher temperature compared to where we are going. So T1 should be minus T, which is that temperature in between the laggings, in between the layers. So 2 pi L K1, this is like we're dealing with a pipe with a single layer, not too many layers. This is how smart it is. 2 pi L K1 T1 minus T over natural log R2 over R1. That's all. So 2 pi, what happened here? Where did we, yeah, sorry. Why did we take the mid pi here? Just put the pi. But I know in the working, we definitely put it there. 2 pi by 0.07 Times the length of the pipe times the K1 and all that. It has taken us elsewhere again. So what we are doing now is here where we have Q dot, we bring 2436.074 equals, then there's 2 pi times the length of the pipe, which is 20. It keeps doing that. Let's do that. Okay, times the 20. Then in the brackets, you have 234.3 minus T. And from there, you will notice that the way you work it out is very simple. You start with what is below here. 0.09 divided by 0.05. Then natural log of that. Whatever you get from there, you multiply by this and this number here, which is 2436.074. And after that, you end up dividing by all these numbers here. Here's just like one quick shortcut. Then you say I'm dividing by 2 pi times 0.07, which is the K1 0.07 times the 20. So from that division, that is where this 162 is coming from. And it will mean that on the other side, you remain with this one exposed, 234 minus T, which means that this 162 can cross the equal sign, and then you say 234 minus that 162.78. The result is 71.5 degrees. 71.5 degrees Celsius. That is our interface temperature. So that is the part 2. We've gone up to question 8. Look forward to the next one. Our next one, of course, has to be fluid mechanics.